Beneath the waters of the English Channel lies one of the most remarkable engineering feats of the modern era, the Channel Tunnel. Stretching approximately 50 kilometers, this undersea marvel links England and France, earning the title of the longest underwater tunnel in the world. The construction, which began in 1988, faced immense challenges, from precise digging to handling complex geological conditions beneath the seabed. 11 massive tunnel boring machines powered through chalk layers, resulting in 3 interconnected tunnels by 1994. Initially estimated to cost £4.8 billion, the final price tag skyrocketed to around £9.5 billion. Despite these obstacles, the Channel Tunnel remains a vital transport link that reshaped travel across Europe and was even recognized by the American Society of Civil Engineers as a wonder of modern engineering. But what made this engineering dream so difficult to achieve? And why is it celebrated with such a prestigious title? Let's find out. This is Megalith. Please subscribe and never miss an update on the best mega projects. For centuries, travelers crossing the narrowest part of the English Channel faced a daunting challenge: turbulent waters, unpredictable weather, and lengthy journeys. This 34-kilometer stretch between southern England and northern France was notorious for its rough seas, making crossings dangerous and often delayed. As trade and travel expanded over time, so did the need for a safer, faster, and more reliable route. The growing economic ties between Great Britain and continental Europe made a permanent link essential, but previous proposals for a connection failed repeatedly due to political disputes, financial concerns, and national security fears. The dream of a fixed connection wasn't new. As early as 1802, a French engineer proposed a tunnel beneath the channel. However, it wasn't until the 20th century that technological advances made such ambitious plans seem feasible. In the 1960s, renewed interest led to more serious talks, but political hurdles remained. It wasn't until 1981 that the British and French governments began to collaborate earnestly. The turning point came with the signing of the Treaty of Canterbury in 1986, which formally committed both nations to construct an undersea tunnel, later known as the Eurotunnel. Construction began in earnest in 1988, with teams working from both the British and French coasts. The project was an engineering marvel, relying on state-of-the-art tunnel boring machines to dig through the dense chalk marl beneath the seabed. By 1990, the tunneling teams met beneath the channel, symbolizing the historic link between the two nations. However, the Eurotunnel faced immense challenges, including water leaks, financial strains, and safety concerns. Nevertheless, progress continued, driven by the potential economic impact and improved relations between the UK and France. On May 6, 1994, the Eurotunnel officially opened, marking a new era of cross-channel travel. Stretching over 50 kilometers, it became the longest undersea tunnel in the world, connecting Folkestone, England, to Coquelles, France, in just 35 minutes. The project wasn't only a triumph of engineering, but a testament to international cooperation, bridging the gap between two historic rivals and reshaping Europe's transport landscape. Today, the Eurotunnel remains a vital link, facilitating trade, tourism, and cultural exchange. But how exactly did engineers achieve this groundbreaking feat beneath the waves? Initially, the project required digging 3 separate tunnels, 2 main rail tunnels and a smaller surface tunnel positioned between them. The main tunnels, each 7.6 meters wide, were designated for train movement, while the central service tunnel, measuring 4.8 meters in diameter, was primarily for ventilation, emergency access, and maintenance. The tunnels were built to run parallel to each other, with cross passages connecting them every 375 meters to facilitate safety evacuations. The meticulous design ensured the safe operation of high-speed passenger and freight trains that would traverse the tunnel. The construction kicked off with the deployment of 11 tunnel boring machines, or TBMs, 5 on the French side and 6 on the English side. These gigantic machines were essential in cutting through the chalk marl, the chosen geological layer, due to its optimal combination of impermeability and ease of excavation. This geological stratum offered a stable digging environment and minimized the risk of water intrusion. On the English side, the chalk marl extended continuously along the tunnel route, while on the French side, the ground conditions varied significantly, requiring different tunneling techniques. As the TBMs advanced through the chalk, the spoil, or excavated material, was continuously removed using conveyor belts, and the tunnels were simultaneously lined with cast iron and reinforced concrete segments. These linings served to provide structural stability, waterproofing, and resistance against the immense pressure from the surrounding seabed. While the English side primarily used open-face TBMs to bore through the relatively dry chalk, the French side faced wetter and more unstable conditions. This required the use of closed-mode TBMs, which maintained pressure to prevent the inflow of water and maintain the structural integrity of the tunnel walls. This approach allowed for safer and more controlled excavation despite challenging conditions. One of the most critical tasks during construction was aligning the tunnels perfectly beneath the sea. Advanced lasers and surveying tools were used to ensure that the tunnels from both the French and British sides would meet precisely in the middle of the English Channel. This alignment required precision to the millimeter, as even a small deviation could have led to significant delays and potential safety hazards. The meeting point of the service tunnel, which was the first to be completed, was celebrated with great fanfare on December 1, 1990, when workers from both sides shook hands for the first time beneath the sea. A symbolic moment marking a historic connection between the two nations. However, constructing undersea crossover caverns was among the most ambitious elements of the project. These crossovers allowed trains to switch between tunnels if necessary, enhancing operational flexibility and safety. The caverns, remarkably spacious, were carefully designed to maintain stability under the seabed. Engineers had to excavate enormous amounts of material while preventing collapses or water ingress. The process involved precise drilling, grouting, and reinforcement to ensure that these cavernous spaces could withstand the pressure exerted by the water above. The service tunnel played a pivotal role throughout the construction. Acting as a pilot tunnel, it preceded the main tunnels by at least 1 kilometer to identify potential hazards such as geological anomalies or high water pressure zones. It was also used to transport workers, materials, and machinery, making the construction process faster and more efficient. Additionally, the service tunnel was equipped with a specialized transport system to ensure quick evacuation and access in emergencies, further enhancing the safety of the entire project. Ventilation and cooling were other significant challenges tackled during construction. The ventilation system was designed to maintain higher air pressure in the service tunnel than in the main tunnels. This pressure differential was crucial for preventing smoke or fumes from entering the service tunnel in the event of a fire. To regulate the high temperatures generated by train movements, a comprehensive cooling system was installed, comprising chilled water pipes that extend along the tunnel's length. These measures ensured a comfortable environment for passengers and reduced the risk of overheating, which could affect both the trains and the tunnel structure. Water drainage systems were also crucial to the success of the tunnel. Pumping stations were strategically placed along the tunnel to remove water from rain, seepage, or accidental flooding. This network of pumps worked in tandem with the tunnel's design features to prevent water accumulation, ensuring the tunnel remained operational even under adverse conditions. The drainage system was designed to handle the immense water pressure from the surrounding seabed, showcasing the detailed engineering that underpinned every aspect of the channel tunnel's construction. Despite the significant advancements and achievements, the construction faced numerous challenges. Technical issues such as unexpected geological variations on the French side and equipment breakdowns led to delays and increased costs. The project was originally estimated at approximately £4.8 billion, but ultimately reached around £9.5 billion by the time of its completion in 1994. Safety concerns also demanded design modifications, adding to the overall complexity and expense. However, the engineering teams remained resolute, adapting to challenges with innovative solutions and maintaining a strong focus on completing the project. The Channel Tunnel's construction overcame numerous technical, financial, and logistical challenges to create a vital transportation link between two countries. And it stands as a symbol of what can be achieved through international cooperation and advanced engineering. If you enjoyed this video, please like, comment, subscribe, and turn on notifications for more exciting content.